Hi, everyone. So today we are going to talk about periodic table trends. So, in the modern periodic table, elements are arranged by the number of protons, which we know is the atomic number. There is a periodic repetition of their physical and chemical properties, which is called periodic law because of the way that they're arranged. And because of this, we can actually see trends in the periodic table. And a trend, remember, is just a pattern that can be used to make predictions. So, like I said, because there's a repetition of properties in the modern periodic table, there are many trends that can be observed. And these actually let us predict characteristics of the elements, and which is why Dmitry Mendeleev was able to, leave blank spaces in his periodic table because he knew that there was a certain element that should go there, but it hadn't been discovered yet. So the first trend we're going to talk about is atomic radius. Now, atomic radius is just the distance from the nucleus to the outermost electron. So just think like if we picture an atom like a sphere, this is the same thing as like the radius of a circle or a sphere, right? It's just the distance from the middle to the outermost electron. Now, as we go across a row of the periodic table, the atomic radius is going to decrease. And the reason for this is because electrons are being entered into the same energy level. Think like the, ring kind of where those electrons are being added. And so as protons and electrons are added, the force between the protons and electrons increases. We saw this in our coulombic attraction activity. If you remember when we had more protons, we have more force pulling those electrons in from the nucleus. So because we have a higher attractive force from the nucleus, because of those more protons, those electrons are going to be pulled in more and thus decreasing the atomic radius. Now, as we go down a periodic table, or a group in the periodic table, or a family, the atomic radius is going to increase because we're adding electron shells. So we're adding energy levels, and therefore that radius is getting bigger and bigger and bigger. Now, another important part about going down the periodic table is that we have this thing called electron shielding. So when we're adding electron shells, the electrons in the inner shells are actually going to shield the outermost electrons, the valence electrons, from the pull of the nucleus. So as we go down a group in the periodic table, the atomic radius is increasing, not only because of the added electron shells, but also because of the electron shielding from the inner electrons. So the next trend we're going to talk about is ionic radius. This isn't really a trend that we see on the periodic table. However, it's just something that happens when an atom becomes either an anion or a cation. So when we become an anion, that means that a neutral atom is gaining one or more electrons. So it's becoming more negative because it's gaining negative charges. And because it's gaining more negative charges, those negative charges are repelling one another. So remember, if we have a negative charge and a negative charge, or a positive charge and a positive charge, like charges repel. So the more negatives we gain, the more repulsion we get. And therefore, adding electrons is going to make an atom bigger because those electrons are going to be repelling one another. On the other hand, if a cation is being made, that means that we are losing electrons. So we have a positively charged ion. And so because we're losing negative charge, there is less repulsion, and therefore the atom actually gets smaller as a cation is made. Now, if we're comparing different ions, say we're comparing something like, oh my gosh, I don't have a periodic table right in front of me at the moment, but say we're comparing two ions that have the same number of electrons. So we know that usually ions are made because they want the same electron configuration like a noble gas. So say we have two ions that have the same number of electrons but a different number of protons, and I'm asking you which one has the smallest radius. Now, the one with the smallest radius is going to have the highest number of protons, because if we have more positive charge in that nucleus, then those electrons are going to be pulled in more. So if they have the same number of electrons and you're trying to compare, just pick the one with the smallest the one with the smallest radius will have the highest number of protons. All right, the next trend we're going to be talking about is ionization energy. And the definition for ionization energy is the energy required to remove an electron from the atom. So electrons are always going to be removed from the outermost or valence shell. And the farther away that an electron is from the nucleus, it's easier to pull it away. And again, we saw this from our coulombic attraction activity, because when we increase the distance from that positively charged nucleus, the force was smaller. So since that nuclear force is smaller holding those electrons, it's easier to pull electrons that are very, very far away from the nucleus off of that valence shell. So with ionization energy, if something has a high ionization energy, that means it's really hard to pull or remove the electron from the atom. If something has a lower ionization energy, it means that it is easy to remove an electron from that atom. Now, ionization energy is going to increase across a row. And remember, this is because the atomic radius is decreasing across a row. So as that atomic radius decreases, those electrons are held tighter by the nucleus because the distance from the nucleus is smaller, and therefore it's going to take more energy to remove those electrons. The ionization energy is going to decrease as we go down a group or a family. And the reason for this is because the atomic radius is increasing. So as that atom gets bigger, it's easier to pull off those electrons or to ionize that atom, because it's a higher atomic radius, it's farther away from the nucleus. That force of attraction to the nucleus is smaller than it is if it was closer. So less energy is going to be required to remove those electrons. Now, when we're talking about ionization energy, you can also think of this in terms of the octet rule. So remember, the octet rule is just that atoms like to have their outermost shell completely full. And we say that when they're full, when they have a complete octet in the s and p orbital of that certain energy level. So something like francium, which I have pictured to the right here, has the lowest ionization energy because it has a lot of energy levels. Like, look at all those rings, right? So many energy levels. So that valence electron is very, very far away from the nucleus. So because it's so far away, it has a very low force of attraction to the nucleus. And because there's only one valence electron, it wants to lose that one valence electron, because that next ring down, see that one valence electron is right here. The next ring down, you can see that there's 8 valence electrons. So there's that complete octet, that next energy level down. So it's going to be really easy to remove this one valence electron so that francium is very, very stable. Now, francium is in group 1, which, if you remember, is the alkali metals. So any element in group 1 is going to easily remove or easily lose one electron, because they only have one valence electron to lose. And that next row down has that complete octet. So they're going to really want to lose that one valence electron. Now, helium, on the other hand, which is the top right, it's in the noble gas group, has the highest ionization energy because it only has one shell. And we know that that first energy level has only the s orbital, which only holds 2 electrons. So since those 2 electrons, it has those 2 electrons, it's completely full, even though it's not, quote, an octet, but it's completely full, that outermost shell, and those electrons are very, very close to the nucleus. So it's going to be really, really hard to remove those electrons from the helium atom. Any noble gases are very, very stable because they have those full outer shells. So they're going to have a really high ionization energy. Now, what we've been talking about so far is just like first ionization energy, but there's also something called second and third ionization energy. Second ionization energy is going to be the energy needed to remove an electron from a positive one cation. So, meaning we have already removed one electron, so now that ion has a positive one charge. Now, if we're talking about something like an alkali metal, remember that is the first group right here. So those alkali metals only have one valence electron. So since they've already removed that one valence electron that they wanted to remove, they're going to have a really high second ionization energy because they're very, very stable. They have a complete octet. They don't want to remove any more electrons because they have a electron configuration like a noble gas. So because of that, it's going to be really, really hard to have another ionization happen. So they have a really high second ionization energy. Now, on the other hand, alkaline earth metals, which is the next group right here, has two valence electrons. So therefore, if we've already removed one of them, then we only have one more to remove to get that complete octet. So they're going to have a really low second ionization energy because they really want that second electron to be removed in order to get that complete octet. Third ionization energy is just the energy to remove a third electron. So we've already removed two electrons now. Now we're going to remove another electron. And so the one with the highest third ionization energy is going to be this alkaline earth metal group because, again, we've removed those two valence electrons that they have, and they don't want to remove a third because now they have a complete octet. Now, the thing that I just want you to remember with the third ionization energy is that aluminum is the one that has the lowest third ionization energy. All right, so that is in this group right here. It doesn't really have a special name, but like the other ones, alkali metals, alkaline earth metals, we have halogens here, we have noble gases, transition metals. This group doesn't really have a special name, but aluminum has three valence electrons. So because we've already removed two and now it only has one more valence electron to remove, it's going to have the lowest third ionization energy. And so here's our aluminum right here. You can see 1, 2, 3 electrons. So it's already removed two. We only have one more to remove. All right, the next trend we're going to talk about is electronegativity. So the definition of electronegativity is the ability of an atom to attract electron toward itself, that it's sharing with another atom. So specifically, we are in a bond here. And in that bond, sometimes if the electronegativity difference is big, sometimes one of the atoms will hold the electrons kind of more than the other atom will. Now here we're going to disregard noble gases because they don't share electrons. They don't bond at all, basically. And so as we go across a row, the electronegativity is going to increase. So this is because smaller atoms with more protons will hold electrons best. So remember, this has to do with atomic radius again. So the closer that those valence electrons or the electrons that are being bonded are to that positively charged nucleus, the higher the force they feel. So therefore, they're going to hold electrons and pull electrons toward themselves more. Now, down a column, electronegativity is going to decrease because, again, talking about atomic radius, remember down a column, it's increasing. So as that atom gets bigger, that means that it's going to have a weaker hold on those electrons. So something like francium, again, we just talked about francium, but it's a huge atom, right? So it's going to have a very weak hold on the outermost electrons that are bonding because those electrons are so far away from the nucleus. They don't have much of a force from the nucleus. So reactivity is an interesting trend because it's going to be different for metals and nonmetals. The definition of reactivity is just the likelihood of an atom to combine with another atom to increase its stability. So for metals, we have to remember that metals want to lose electrons when they react. So metals, remember, are on the left-hand side of the periodic table. And so something like an alkali metal, remember, only has one valence electron. Alkaline earth metals have two valence electrons, which is our second group. And so the alkali metals want to lose one electron, the alkaline earth metals want to lose two electrons, and so on and so forth. So as we go down a family, the metal reactivity is going to increase because added energy levels are going to decrease the attraction between the nucleus and the electrons, making it easier to remove those electrons. So again, think francium, right? Francium is in the first group. It's all the way down that family. It's going to be really, really easy to remove that one valence electron from francium because it is so far away from that nucleus. And so it doesn't feel much of a force of attraction toward the nucleus. And as we go across a row, metal reactivity is going to decrease because as we add protons, it's causing a greater force of attraction. We can also think of this in terms of valence electrons. So like I said, the alkali metals only have one valence electron. It's going to be easier to remove just one valence electron than it's going to be to remove, two valence electrons from the alkaline earth metals. So those alkali metals are so incredibly reactive that we really don't see them by themselves in nature at all. They're going to immediately react because they're so reactive. Now, on the other hand, nonmetals want to gain electrons when they react. So remember, nonmetals are over on the right-hand side of the periodic table. To the right of the staircase, and our halogens are all nonmetals. Of course, noble gases are nonmetals, but those don't react at all. So we're kind of disregarding those when we're talking about reactivity. But because nonmetals want to gain electrons when they react, the reactivity is going to decrease as we go down a family because, again, those added energy levels are decreasing the force of attraction to the nucleus. So it's going to be harder to gain an electron when we go down a family. Now, on the other hand, as we go across a row, the reactivity is going to increase because those added protons increase the attraction for electrons. Again, you can also think of this in terms of valence electrons. So the halogens are in group 7. They have 7 valence electrons. It's going to be really easy to just get one more valence electron for that complete octet. Now, the next group over, which is like the group that oxygen is in, only has 6 valence electrons compared to 7. So you need to gain 2 more electrons to get that complete octet. So it's going to be a little harder to gain 2 electrons than it is to gain 1 electron. So the halogens are going to be more reactive than that oxygen group. Again, like I said, we're not including the noble gases here. So this is kind of what it looks like. The reactivity is going to be opposite, obviously, for metals and nonmetals because metals want to lose electrons, whereas nonmetals want to gain electrons. So electron affinity, the definition here is the amount of energy that's liberated when an electron is added to a neutral atom to form a negatively charged ion. So I want you to think of this basically as how much an electron wants to gain, or how much an element wants to gain an electron. If it has a high electron affinity, meaning it wants to gain an electron really, really bad, that means a lot of energy is being released when it gains an electron. So it's like a good thing, and it releases energy because it gained that electron. Now, again, we're going to disregard noble gases here because their outer shells are totally full, so they don't want electrons at all. But disregarding those noble gases, the electron affinity is going to increase as we go up a group, and it increases as we go from left to right on the periodic table. So something like the halogens and fluorine in specific have a very strong electron affinity because if they gain just one more electron, they have a full shell. Now, fluorine at the very top of the halogens is the smallest halogen. So because it's so small, that valence shell is very, very close to the nucleus. So it's really feeling that attractive force from the positively charged nucleus. So it's going to be very easy for fluorine to gain that one more electron. So when it gains that electron, it's going to release a lot of energy because it has a high electron affinity. Now, on the other hand, the group 1, which is the alkali metals, and group 2, alkaline earth metals, we don't want to gain electrons here because we would rather lose electrons. So therefore, we have a very low electron affinity for the alkali metals, alkaline earth metals over here on the left-hand side of the periodic table.